Hi, I'm Reece Coleman, Waterways and Wetlands Research Manager in the Applied Research team at Melbourne Water. And thanks for joining us for another edition of Melbourne Streams, where we've been talking everything waterways and wetlands research. I hope you've been enjoying these presentations that we've been releasing each day. And I'm super pleased to round out the first week with a talk from Dr Yung En Chee from the Melbourne Waterway Research to Practice Partnership with the University of Melbourne. Yung is a quantitative applied ecologist. Her research interests include spatial and ecological modelling, decision analysis, reasoning under uncertainty, and interdisciplinary research. She works on how ideas and methods from these fields can be integrated to improve conservation and environmental decision making. Yung's talk is a really great summary of how we built and applied habitat suitability models and used them in the Healthy Waterway Strategy 2018. The talk covers what are habitat suitability models, what data was used to build them for aquatic macroinvertebrates, fish and platypus, what are the likely impacts of urban growth and climate change on in-stream biodiversity, what are the most cost-effective actions to deal with these impacts, and how do we support co-design with stakeholders to prioritise where to focus our efforts for biodiversity gains. This project is part of a broader project. We're also currently developing habitat suitability models for wetlands, in this case for frogs and for birds, and we hope that they'll be ready for the midterm review of the strategy. The use of habitat suitability models in our strategy has been a great step forward because it's allowed us to really make use of all the great data that we've been collecting over the past 20 or more years. And it's also allowed us to set quantitative targets in the strategy. If you have any technical questions about Yung's talk, then feel free to contact Yung directly. She's provided her contact details. If you have broader questions about the Melbourne Waterway Research to Practice Partnership or the Waterways and Wetlands Research Program in general, then feel free to contact myself or Slobodanka Stojkovic from the Waterways and Wetlands Research team. Of course, you can also visit now our new research hub. So if you go on the intranet and search for Research Hub, you'll find it. And there you can browse all the waterways and wetlands research projects that we've done in the past 10 years and the outputs coming from those research projects. And shortly, all the reports and projects for the other research portfolios will also be there. We hope you enjoy this talk and we look forward to providing you more next week. Thanks.
Hello, my name is Yung En Chee and I'm a Senior Research Fellow at the University of Melbourne. As part of the Melbourne Waterways Research Practice Partnership, I worked with my colleagues Reece Coleman, Sharon Ross-Rakesh, Nick Bond and Chris Walsh on this project to see how we can use and integrate best available data on animal surveys, environmental characteristics, management actions and costs to inform priorities in Melbourne's Healthy Waterways strategy development process. I'll try and step you through and explain how we supported this process. First of all, I'd like to acknowledge and pay my respects to all the traditional owners and elders past and present who have long cared for the lands and waters that this research addresses. From the west to the east, this includes the Waterway people, the Wurundjeri people, and the Bunurong people. Usually these strategies are done every 5 years, but this time around, Melbourne Water wanted to consider the long future. They wanted to undertake systematic and strategic long-term planning to explicitly consider climate change and urbanization impacts, and to do so with a lot more community collaboration than they had in the past. So the challenges. When you have thousands of kilometers of waterways, how can we take a systematic and strategic approach to in-stream biodiversity conservation? And how do we give managers and community members the relevant background, information, data, analyses, and so on to deliberate issues, opportunities, challenges, and trade-offs? To support the process, we developed a suite of tools, spatial tools, our family or species habitat suitability models, and a spatial prioritization analysis. And in this talk, I'll tell you a little bit more about each one of them. But basically, the idea of and the point of all this work was to make sure that we use these tools to help managers and community members understand the biodiversity patterns in streams across Melbourne, to help them explore climate change and urbanization impacts on in-stream biodiversity, to help us all quantify the benefits of management actions, and to identify cost-effective management actions across Melbourne streams. And finally, to identify priority locations at which we should focus efforts and energy. So let's have a quick intro to the spatial tools here. So this is the digital stream network that we've developed to represent waterways in the Melbourne Water region. There are over 8,200 stream reaches. And for every single stream reach, we have hydrologically delineated the sub-watershed that drains to it. What this means is that for every reach in the network, we are able to characterize the influences that affect it at a range of scales. So for instance, in this subset, we can characterize the pink area, which is the riparian zone of the reach. We can describe the yellow area, which is the immediate watershed of the reach, and we can characterize the entire upstream contributing watershed, which is the green plus the yellow areas bounded by that solid black line. And this helps us capture and account for influences on a reach that operate at multiple scales. And we'll see later on why this is important. Another good thing about this digital representation is that it allows us to do analyses at the finest scale of the reach, which is what tends to be most relevant to on-ground management. But it also allows us to group and to summarize information at different levels of interest, such as the management unit and the catchment level. And this is useful when we want to do, for example, reporting. Right, so that was the digital stream network. Now we come to the habitat suitability models for our in-stream animals. We're really lucky to have over 20 years of good quality data on macroinvertebrates, on fish, and on platypus from a variety of monitoring activities that Melbourne Water has undertaken over a long period of time. We use this really valuable resource to build habitat suitability models for 52 macroinvertebrate families, 13 native fish species, and the platypus. So what you'll notice from this map is that although we have a pretty good distribution of surveys across the Melbourne Water region, there are nevertheless some gaps in the sampling coverage. And that's why we build these models, so that we can estimate in-stream biodiversity at the unsampled streams. Now, to describe the in-stream environment of each reach, we use 10 to 12 ecologically relevant descriptors, including variables that can be used to help us explore things like climate change, urbanization, and the effects of management actions. So these maps here show how 4 of these environmental descriptors vary across the Melbourne Water region. And here's a quick overview of the habitat suitability modeling process. For each species, we extract the environmental data at survey sites where it is present and where it is absent. And then we combine this information and take this into the modeling process, where we analyze the relationships between the environmental characteristics at sites where a species is detected and also where it is not detected. And we use this to develop a quantitative model that predicts how suitable any given stream reach is for each species. So in essence, the habitat suitability models enables us to go from discrete point location data to spatially continuous estimates of habitat suitability for each species. And we built individual models for each of the 52 macroinvertebrate families, 13 native fish species, and platypus. So some of the future threats we expect will include warmer temperatures, drier conditions, and increasing urbanization that creates increased stormwater runoff from impervious cover. Now the question is, what does this look like across our streams? For the Yarra catchment, this is what a fairly modest 1.5 degree temperature increase looks like. As you can see, it looks like quite a dramatic change. And again, for the Yarra catchment, this is what drying, equivalent to about a 25% reduction in the flows at the mouth of the Yarra, looks like. Again, a fair bit of impact that we might expect. And finally, with respect to urbanization, this is what the future distribution of urban areas in the Yarra catchment looks like based on current information in the planning scheme zones data. There's big expansion in the northern corridor and smaller pockets of urban development scattered across existing built areas. So with climate change and urbanization impacts, we expect in-stream habitat for animals to decline under a business as usual future. And the important question is, what can we do to change the trajectory? So instead of showing you the impacts on every single species, I'm using a condition index that integrates information across all the macroinvertebrate families, all the 50 plus families. So blue and green indicates very good and good condition respectively. And at the other end of the scale, red indicates very poor condition. If climate change and urbanization impacts occur together, which is what we're calling our business as usual future, then this is what we expect in-stream macroinvertebrate condition to look like. There's general decline in macroinvertebrate habitat under a business as usual future, particularly in the upper reaches of Merri Creek, where a lot of future urban development is expected. But declines are also expected in tributaries of the Middle Yarra and some tributaries of Cockatoo Creek and Warrialloc. And what we have here on the bottom right is a bar chart that summarizes the amount of stream length that is in each of the condition categories. And this is a useful way to be able to compare the conditions across different spatial areas. So we have our business as usual future conditions, but what are some of the main actions that we can take? Well, broadly speaking, we can revegetate riparian areas. We can make sure that we effectively manage stormwater in future urban areas. Or we can do some combination of the two. So let's see what difference these actions could make relative to the business as usual future that we face. So we use these difference maps to summarize changes relative to the business as usual future. We use this diverging blue, white, and red scale to show the difference made by any given action. So blue means improvement relative to the business as usual future. Red means deterioration relative to the business as usual future. And that's the sort of whitish colors in between mean little or no change relative to the business as usual future. And what we can see here is that revegetation to 20 meters width on its own benefits streams in the tributaries of the Middle and Upper Yarra, including tribs of the Cockatoo Creek and upper tribs of the Plenty River and Diamond Creek. And again, we have on the bottom right, our bar charts that summarize the lengths of streams in each of the condition categories. And as you can see, revegetation on its own does improve conditions relative to the business as usual future for macroinvertebrates in the Yarra catchment. Now, if we can effectively manage stormwater from all new future urban areas, that is all this dark gray area, this will be beneficial to macroinvertebrate habitat downstream of the areas stretching from Wallen in the north down to Craigieburn. So, but as you can see, the sort of benefit expected from this is relatively less than expected from revegetation. Now we can also look at what happens if we combine those two mitigating actions, revegetation to 20 meters width, as well as effective stormwater management in all future urban development areas. And this map shows us the benefits if we do both of those actions together. And what we can say is that the combined management actions are much more effective than each one of the actions on their own. So these sorts of explorations that we just sort of gone through are what we use to help managers and community workshop participants appreciate some of the key messages for the Yarra catchment. Basically, that macroinvertebrate habitat is likely to be degraded under a business as usual future. Effective stormwater management for all future urban areas, especially in that large northern development corridor, can definitely help, and it can even, in some cases, improve macroinvertebrate habitat relative to the business as usual future. Revegetation on its own seems to produce the most macroinvertebrate habitat benefit at tributaries of the Middle and Upper Yarra, at tributaries of Cockatoo Creeks, and tributaries of Plenty River and Diamond Creek. And finally, the benefits are greatest when actions like stormwater management and revegetation are combined. So what should we do and where, given the range of threats? As we saw, we can estimate and map the distribution of threats across the Melbourne Water region. We can consider mitigating actions that are broadly applicable across the region. And we can use a bunch of tools to help us explore the expected costs and benefits of actions, and therefore help us prioritize actions to cost-effectively maximize in-stream biodiversity across the region as a whole, across all 13,000 square kilometers of the greater Melbourne region. And that brings us to the spatial prioritization analysis using a piece of software called zonation. This software was originally developed at the University of Helsinki in Finland, but it has now been used in sort of conservation planning applications in Australia as well as worldwide. So it's a well-accepted piece of software. So coming back to our question. Knowing that stream biodiversity values and threats vary across Melbourne, we want to figure out what action we should take and where specifically we should focus our efforts. So we approach the task like this. First of all, we identified the most cost-effective action at each reach. And we generate a map of most cost-effective action across all of Melbourne's streams. We use our habitat suitability models to apply the most cost-effective action at each reach. We use our habitat suitability model predictions to compute the benefit due to an action, the most cost-effective action. And then we analyze the species or taxa species-specific management gains, plus other inputs using the spatial conservation software and zonation. And once we've done that, we are able to generate a map of streams ranked by priority for taking action. Don't worry if this sounds like a lot, because we'll step through this in the next few slides. So we focused on 6 candidate actions. Revegetation of the riparian zone to 20 meters width on both sides of the stream. Managing stormwater from future development only. We call this no additional stormwater impact. Managing stormwater from existing and future development, and we call this removing all stormwater impact. And then some combination actions, so revegetating the riparian zone to 20 meters width, together with no additional stormwater impact, and revegetating riparian zone to 20 meters width, and removing all stormwater impact. And finally, we have 6th candidate action, which is essentially this, maintaining the status quo. And this is the case for some reaches where the vegetation is currently intact and there is no existing development, nor is there any planned future development expected in the catchments of these reaches. So the next thing that we need to do is to estimate the cost of each candidate action at each reach. Now, the first piece of information we need is to estimate the unit-based costs of the action. So for revegetation, this is the cost per kilometer, which also includes the cost of any woody weed removal, if any of it is present. And the unit-based cost of an action will tend to vary depending on where you are in the landscape. For instance, it is more costly to revegetate in the west and in urban areas than it is in the Yarra, and it's cheaper again in the southeast region. And the reasons for this relate to things like access and terrain, whether there's a need for livestock fencing to exclude predators, whether there's a need for weeding and supplementary maintenance like watering in the first year of vegetation establishment. So it varies depending on where you are in the landscape. And once we have unit-based costs, we then need some specific reach level information to estimate the cost of an action at that reach that we're interested in. So for this means, with respect to revegetation, this means getting information on the length of the reach that is covered by woody weeds, and as well as estimating the length of the reach that's currently unvegetated. And we use remote sensing data to estimate both of these two pieces of information. And it's a similar story for stormwater management. In the first instance, we need a unit-based cost, and that varies depending on whether we're talking about retrofitting to treat existing impervious cover, or whether we're dealing with expected future impervious cover. It's more costly to treat existing urban cover. And then we need some specific reach level information and data on how much existing and how much future impervious area there is in the contributing catchment area of the reach. So for instance, in this figure, if we want to know what the impact is going to be on this target reach, we need an estimate of the amount of existing impervious cover in its contributing catchment, as well as the amount of future impervious cover expected in its contributing catchment. Okay, and we basically have to do these calculations for all of the 8,200 plus reaches across Melbourne. Okay, so how do we then identify the most cost-effective action for each reach? Well, first of all, we calculate the benefit of each candidate action at the target reach. Because we're concerned about biodiversity, to us, benefit is that positive change in habitat suitability for each species in the target reach due to the candidate action. So sometimes we also want to give extra weight to a species that is threatened or endangered, and we can do that using this weight term in the equation. Benefit due to a candidate action is summed across all the species that we have habitat suitability models for. All right, so this N is that 52 plus 13 plus platypus. Once we have calculated the benefit associated with each candidate action, so this term here, we bring in the cost of implementing the candidate action in the reach to this denominator, and we get an estimate of its cost effectiveness. So the cost effectiveness of the candidate action. Then essentially, we repeat this calculation for all the different actions, candidate actions that we have. And then we compare the cost effectiveness estimates across our 5 candidate actions and identify the most cost effective action for that given reach. And again, we repeat this exercise, this calculation, for all 8,200 plus reaches that we have across Melbourne. And after going through these calculations, this is the resultant map of the most cost-effective action at each reach, right? But our budget limitations mean that we can't just go through and apply the most cost-effective action at every reach. We still need to figure out where in this landscape we should take action first of all. And this is where we turn to our zonation software tool. So having accomplished the first 2 steps in the blue boxes, we use zonation to carry out the next 4 steps. Essentially, we use zonation's capabilities to make sure that we account for representativeness, that is, all the model biodiversity, all the species and families that we have models for. We use it to account for irreplaceability, which takes care of species that are unique or rare in the Melbourne Water region. We use it to take care of species that, as we say, we might want to upweight because they're of a special conservation status. And we can also use zonation special features to account for any sort of upstream and downstream connectivity requirements of particular taxa. So for example, migratory fish that need to move between headwaters and the ocean. And the final output of these 4 steps will be a map of stream reaches that are ranked by priority for taking action. And this is what it looks like. This is the zonation ranking solution where the darker colors show increasing priority for action. It shows where we should act first to maximize biodiversity by protecting what is currently good, what's expected to be good under business as usual future, and also where actions make the biggest positive difference. So what's really nice about this is that it provides a continuous ranking of priority of reaches across the Melbourne Water region, which is a big help if you have 8,200 plus reaches. So essentially, these 2 maps are used together, and you can cross-reference between them to identify for each high-ranking reach what is the most cost-effective action at that particular reach. And both of these maps were used together for Healthy Waterways Strategy Priority Action Planning, and also to help with the target setting. Now, I need to stress that these 2 maps of cost-effective action and priority action help to integrate a lot of data and knowledge to help provide decision support. But it's really important to stress that they did not dictate the strategy action plans and targets. So they really were part of a larger process. all the top-ranked reaches were, and their actions, their corresponding actions, were reviewed through a checks process by Melbourne Water staff. They were also compared against community workshop action proposals to identify where community actions matched our high priority in areas. And wherever possible, there was a process to make sure that we tried to align community co-designed actions with the computationally derived priorities. And Melbourne Water made a big effort to address the feedback with over 1,800 comments that were received as a result of presenting the preliminary targets to the community. I should also say that the frog, bird, and vegetation values, which were not in-stream values and were not modeled, were also considered and accounted for. And so were water quality and environmental flow risks. So as I was saying before, there's a larger process that wrapped around the modeling work, and that also included consideration of social values and livability aspirations. And all of those things collectively informed the targets and performance objectives for each of the major catchments. And that's what you read about in the reports for each of the major catchments. And so we've come to the end of that. Thanks very much for listening. You are welcome to contact me at my email address. And if you'd like more information, we have a short version, which is a conference paper that's available, and a much longer version of an account of this modeling work in the form of a resource document that you can also download at this particular link. Thank you very much.